Dear students, I welcome you all for the online learning platform for the course Warehousing Automation. So, in this particular semester, we are learning this particular course for the honors and honors registered students, and within which by means of series of lectures we have completed 2 units. So, prior to it, we have completed 2 units. The first was warehouse process, and the third unit we had as a sequence, and we finished planning and implementation. So now in unit 2 we'll discuss about queuing theory. So basically, what is queuing theory? What is a queue? How a queue as an association with warehouse case, and how automation and warehouse are going to be integrated with a queue, and how a problem is being formed and how it is being solved. So these all are the core discussions what we are going to have in this particular unit. So in the series, when you see, it is a third unit, but in the order as a syllabus, when you see, it is going to be unit 2, queuing theory. So now we'll get into the contents for unit 2. So there are total 8 chapters are there. So first chapter starts from concepts and terminologies what we use in a queuing theory. Then it goes to queuing models, and this number what you see here, this is called as Kendall's notation. So you will learn everything in detail in the upcoming presentations. So how to analyze or how to form a problem with respect to order picking and packing, we'll see. Then the bottlenecks, or how to identify the congestion points, which all are the points which acts as an hindrance for the performance of a queue, we'll see. Then how such service level management can be done. Then how average waiting time and queue length is going to affect the process, we are going to see. And we are going to forecast the queuing behavior and demand, and proactive identification and mitigation. So these all are the chapters what we have got in unit 2, and this particular presentation will take you to concepts and terminologies. So what is a queue? So before we get into this queue, to understand it, I hope everyone would have experienced a queue somewhere or the other. Maybe as an individual, or in a system, or maybe in a vehicle. Anywhere you would have seen a queue, you would have experienced a queue. So what queue in general term means? It is something, a process where we wait for the case of service. This is what generally we understand. Clear? But now from a technical point of view, let us understand what is a queue. So a common situation that occurs in everyday life is that of waiting in a line. It's basically waiting in a line. We have got a line and we are going to wait either at bus stops, petrol pumps, restaurants, ticket booths, doctors' clinic, or bank counters, traffic light, and so on. So in a country like India, where queue is inevitable in any process, you get into any process, you get into any system, obviously queue is going to be a mandatory part. You can't even bypass some cases. You are supposed to stand in the queue, you are supposed to wait for a while, and you are going to get the service done. For the intent of the service will be solved, till then we are going to wait in the queue. So now in a workshop, in a warehouse case, okay, so how do we consider here means the machines are going to wait, okay, the workpieces are going to wait for the case of getting machine, or in other case means in our own warehouse case means, so items wait for the case of order. So they will be waiting in the rack, and from the rack the moment order comes, that particular product will be taken and it will be packed nicely. So likewise, waiting is going to be inevitable into the process. Okay. So warehouse is also having a queue, and the product is going to be cured, and it is going to be packed, or it is going to be dispatched, whatever may be the thing. So nicely a queue is going to exist. It's going to persist in the process. In general, a queue is formed at a production or an operation system when either customers, being humans or physical entities, requiring service wait because number of customers exceed the number of service facilities, or service facilities do not work efficiently and take more time than prescribed to serve a customer. Okay. So what is this is why the waiting time comes. That is what this particular definition takes us through. Now in a very simple case, now let us take in the case of a canteen. So the canteen is like this, where we go to in our own college canteen, we take the plate, we go to the server and we wait. Why? Because people are standing already in the queue. There are people standing in the queue. Say for example, some 4 members are waiting. So they need to collect the food. Okay. Till then, till our turn comes here, we need to wait. Now, how can this be defined as the way or the operation where we get the food, right? The place where we get the food, and that is called as service. That is called as service. Okay. So the person who serves us is going to be called as service facility. Okay. So food, till we get the food, that is going to be called as service, and the person who gives us food is called as service facility. Now, why do we stand in the queue? Maybe 2 reasons. Okay. Reason number 1, where the service facility is giving poor efficient, that is, he is not highly efficient, he is taking good amount of time to serve the food. Number 1, that might be reason number 1. When he is having plenty of food, okay, for example, he is having some plate full of dosas or a pongal being kept into a pot, okay, so he has to pick and right quantity he has to serve, so he is very slow, or some lack of tool, something like that. Okay, so it is human oriented. Now the other case, the second reason for poor service facilities is not at all having, maybe some days you would have seen puris will be in a piping hot, it will be brought from the kitchen. Okay, till the arrival people are supposed to wait. Now the problem is not with respect to the service facility, the problem is with the availability of service. The food is not available, henceforth it is not being served. So till then the person, that is service facility, is going to wait. Okay, as a customer we are going to wait, and we are in want of service. So 2 reasons. Reason number 1, poor functioning of the service facility, that is the person who serves, and second thing is we don't have sufficient quantity of service. Okay, so these all are the 2 things, and this is what the thing. So I will again go back. So in general, people wait because number of customers exceed the number of service facilities. So only one person is going to serve, number would have been gradually increasing, so you will not be able to do in a very faster case. Or other reason, service facilities do not work efficiently, take more time than prescribed to a customer. So everything is available but he is very slow. So these all are the 2 reasons. One thing is number of queues more, service facilities lacking, and second thing is we don't have an efficient system. So these all are the 2 reasons why there is an accumulation into the queue. On the contrary, if everything is smooth, okay, so food is being properly brought within least possible time, and everybody, that is service facility, is very fast, means obviously there is no need of a queue, there is no need to wait. Clear? So this is the takeaway from this understanding. So now, where to use this queuing theory? So queuing theory, theoretically speaking, it can be applied to variety of situations where it is not possible to accurately predict the arrival rate. Number 1, of customers, arrival rate of customers, and service rate of service facility or facilities. So 2 terms here we are coming across. The first thing is arrival rate, and second thing is service rate. So both these things are very important. Arrival rate. Again, I will go back to the same canteen example. So morning somewhere from 7:50 to 8:05 or 8:10 is the duration where we get more number of buses arriving into the campus. Now, can we fix any sort of particular pattern? Once in 2 minutes we'll get a bus, or once in 10 seconds we'll get, no, nothing like that. It is based on traffic. Okay, we can't fix any sort of arrival pattern. There is no particular pattern, and that is called as arrival rate. And service rate is the moment when bus comes, all of a sudden all will not be coming to the canteen. Few will go to their classrooms, maybe they keep the bags, then they come back. Some faculty members will go for punching, then they come back. So both these things need not to be the same. So both will be differing. Arrival rate and service rate will be differing. So how probability comes into picture, how arrival rate is fixed or it is assumed, then how service rate is calculated, we will see everything in the upcoming presentation. So 2 things now. The first thing is why, what is the reason for waiting in the queue, we just saw, and the second slide it took us to arrival, 2 new terms, arrival rate and service rate. So in particular, it can be used to determine level of service, either the service rate or the number of service facilities that balances the following 2 conflicting costs. Okay, so now before I get into this, again I will come back to the same example. How to minimize the waiting time and how to increase the service rate. Now in the canteen, same example, there is one person, that person is called a serving facility. So he is going to serve food, and that serving of food is called as service. How to minimize the waiting time and how to maximize this service rate? If you have two people, okay, let me arrange like this. We have got two people. When they serve you, whether the time will get reduced? Yes, obviously the answer is correct. If you have got three people to serve food, obviously the service rate is going to be extraordinarily good and waiting time is maybe null. We can assume that to be null. Okay, that can be considered. And second thing is, can you plan properly and permit only requisite number of people in the prescribed time? Yes, again it is okay. But again, people will be waiting elsewhere, may not be inside the canteen, somewhere they will be waiting elsewhere. So how to govern this particular thing is, that's where cost comes into picture. The first thing, cost of offering the service. So you have got two people to serve. Maybe per day we are supposed to pay wages for them. When you have got two person, obviously twice we are supposed to pay. When we pay twice, obviously that cost what we incur will be directly levied onto the product cost, okay, the cost of the food. So that may not be agreed by the customers. And second thing, cost incurred due to delay in offering services. So you are having some sort of delay to offer the services, obviously we are going to lose our reputation. Of course, this is canteen, this is going to get adjusted maybe within few minutes, but when you get into real world scenario, industrial scenario, yes, there is going to be a penalty charges if you are not sticking to time. Okay, there are several examples are there when we are unable to honor the commitment. Obviously we are supposed to be paid some sort of fine. We need to pay fine in this regard. Okay, so that's where queuing theory is very, very important. So this is one particular simple diagram which associates everything. So now how to interpret this? So we have got two axes. So this axis X is going to take us to level of service. Okay. So starting from 0, it is going to be a good service and gradually it goes to poor service. And similarly, cost of operation, here initially it is low and it gradually goes to high cost of operation. So now we'll see the first case. So this particular line is cost of waiting per customers per unit time. So initially, once the cost of operation, okay, is high, that means you have got 2 or 3 servicing facility, means obviously level of service will be extraordinarily good. Okay, immediately they come, you have got some 3-4 counters, they get everything done and then they go off. So cost of operation will also be high because we are having some 3 or 4 counters. On the contrary, we'll go for the same to the other, cost of operating the service facility per unit time. So initially the time will be low because you are having poor cost. So initially I've got only one counter. So obviously the time will be very, very high. So the cost of operating, obviously it will be low because we have got only one. But the moment when you increase the number of counters, obviously the cost is also going to increase. So then these two things are corollary to each other. The first case, service is good. On the other case, cost is also high. So now both should go have a common case called as optimal trade-off, and that is where we should calculate total cost. And at one particular point of time, where graphically where both these lines merges, we are going to get a break-even point. This is the break-even point which is mutually agreeable by the customer, by the service provider. So both these people are going to commonly consider this particular point, and that point is called as optimal operation cost. So it will be mutually agreeable by the service provider as well as by the customer. So this is what this particular graph teaches. Now, very simple cases where we wait for some service. Okay. So from in a real life, not from an industrial background, from a real life example. So first we go to petrol pumps. So we wait. So there are so many cars or two-wheelers being stagnating in the queue. Yes, we need to wait. What is the service we wait for? It is for the availability of pump. Okay, petrol pump or diesel pump is going to be there. Of course, now CNG, LPG, there are several services are there. So we wait till the facilities made available. So whomever is standing ahead of us should get served, then only we can go. Now think of one particular situation, you have got multiple being, that is service facility means obviously the queue length is going to be low. So this is where we should come out with some sort of inference. Second thing, obviously hospital. So hospital means patients will be there, maybe for the case of to meet the doctor, in the pharmacy, for the lab, whatever may be the thing. Airport, yes, airport, what is the service facility here? To board the flight. Not only to board the flight, you are boarded the flight, some 10 flights are there. On a priority basis, they will be allowed to use the runway. Once you allot the runway, then only the flight will be in a position to take off. So the service here ultimate, okay, not to just board the flight. Ultimate is to get the runway. So this is where we need to know what is the ultimate service by which the system can completely close the loop. So runway. So post office is sorting and then it goes to us. The job interviews, some particular order will be there. Then cargo. So thanks, cargo is our none other than our warehousing automation case. So workshops, yes, machines are going to be idle for the want of workpiece, some cases for the want of workpieces or labors, whatever may be the case. So in a factory, there are several examples, maybe inside cafeteria, canteen, or to punch, that is biometric cases, for some want of some attendance monitoring system, something like that. So these all are the regular day-to-day queue what we can go ahead or what we would have faced. The structure of a queue system. So now how to structure a queue? So this is very, very important. Why? Because that is where we are going to mimic the physical system into a mathematical system. Mathematically, we want to represent the system. So this is how the structure goes on. So these are the major components or parts or elements, whatever we call. Yes, these all are the major things. The first thing is calling population. This is very large, maybe finite or infinite, that we'll see in the upcoming slides. So calling population, so from where? Calling population means from which particular lot are we going to get the customers? Are they going to be in unfew numbers or they are going to be infinite? We don't know. So that is calling population. Second is queuing process. So they came for a service and how are they going to wait in the queue? The pattern how they are going to wait in the queue is called as queuing process. And queue discipline. You can't blindly believe that all will be disciplined inside the queue. They might be having some sort of behavioral aspect that also to be considered in a queue. And service process or mechanism. For what purpose are they waiting here? Okay. How are we going to serve them? Are you going to serve them physically or digitally, or you have got some sort of services of newer kind? So all such things falls under this particular category. So this is how a queue is going to be represented graphically. So calling population, so this calling population is one a society or some sort of region can be considered. So they are going to be the input source. So they come into the process. So on the arrival, they come into the system. On the case of arrival, so you can expect bulk. Okay, you can expect bulk in this particular case. So these are queuing behaviors. There are three queuing behaviors. We'll see one by one. So they come into the waiting area, they wait. Clear? So this is how our queue comes inside. So here the waiting line is none other than our queue. So how the queue discipline is going to be there. So on the arrival, customers are going to exhibit bulk. In the waiting area, they are going to renege. They are going to exhibit a behavior called as renege. In the queue, now waiting is over, now they arrived the queue and they will be exhibiting a behavior called as jockey. Now they got to the service facility, they got their service done and they go out. Okay, so this is a graphical representation of a queue. Now we'll see the behaviors. So calling population characteristics. Now what is the size of calling? Okay, what number of size do you expect? Behavior of the arrivals, what is their arrival rate and pattern of arrivals. So these things helps us to characterize as well as to model and design a queue. So first, size of a calling population. How to know this? In our example, let us take a college. Okay, in our college we know there are some 200 plus faculty members are there, some 100 plus non-teaching staff members are there, and some 1000, say some 3000 students are there. So now this is our finite strength. So daily the maximum strength what you can expect is students of 3000 numbers, 100 numbers of staff and 200 members of teaching faculty members. So this is what our population is all about. Some population might be increasing because now admission season, so maybe people of first years who intend to join the college might be in the process of coming. Okay, so again it is going to be a finite. But on the contrary, when you see Tamil Nadu is having some 8 crore or 7 crore of population, so now our calling population is not this 8 crores or so, only this some thousand, say 4,000 or 5,000, that is our calling population. So only from this population we are going to get customers. That is, customers are none other than students, faculty members or whomever. They come for the service facility, and here the service facility is college. Okay, the service is transfer of knowledge. So this is how a queuing system is designed. Now on the contrary, we'll take up a toll plaza. Okay, toll plaza. Now can you give some any predefined population for them? No. From the country, not the state, from the country, even from foreign countries are also possible. So people will be coming from any geographical location. So such thing is called as infinite. Okay, it is called as infinite. But in our case, college case, only we have got some few thousands. So that is called as a limited population or finite population. Only from this population we can expect daily to the college. Okay, some few percentage may be beyond this population, but anyhow it is restricted. But as such, when you take a toll plaza, you can't fix some numbers in this regard. Next, behavior of arrivals. So under what case or how do they behave here? So now let us take a very simple case. We would have stood in a queue for a long while. What usually we do? Think of first thing is you just calculate virtually. Now there is only one counter is there, some 100 people are standing in the queue. Some cases you may not feel to stand in the queue, okay, or you are standing in the queue. All of a sudden a next counter has been opened. What will be our behavior is we try to migrate from the queue which originally we were standing, and we try to go to the next queue. So bypass, okay. Likewise we jump from like this, or some cases we get frustrated and we leave the queue. So likewise many things are there. So we'll see how the queue is going to behave. So first thing, balking. So balking customers do not join the queue either by seeing the number of customers already in service system or by estimating the excessive waiting time for the desired service. They come and see, they look, they just gradually they observe what is the queue length, what might be the, they themselves, they see, they don't know the actual thing, they just by visually by seeing, they come, they draw inferences, and they don't join the queue at all. They are not at all interested for the service. So such is called as balking customers. Second, reneging customers. After joining the queue, wait for some time in the queue but leave before being served or on account of some reasons. They join, they stand for some while, and they get frustrated and they just leave the queue. They are not interested for the service. So reneging. So balking means they look into the system, they calculate on their own, and they don't gain confidence and they don't join the queue at all. Second case, reneging. Reneging, what they do is they come, they get into the waiting line or the waiting area. But after seeing some reasons, because of some reasons, they get frustrated and they just leave the queue as such. Then the third behavior is jockeying customers. Jockeying customers move from one queue to another, hoping to receive service more quickly. Okay, there are some two counters are there. One counter is not at all moving and second counter is going on moving, means it is very natural that they migrate from one to two. So usually we can see this in a railway booking. Offline cases we can go ahead with. So these all are the three behaviors of a customer. Now pattern of arrival. Pattern of arrival means, do we have any schedule? 5 o'clock one person will come, 5:01 somebody else will come. So once in 10 seconds or once in 60 seconds we can expect? No. So pattern here is with respect to how the customers come into the queue. Either they may be batch or they may be individual. Individually people might be coming, or they might be coming in terms of batches. So how do they come to the system? So that is what we go ahead with. So two things we can classify. First thing is either as a batch or as an individual, and second thing is in a scheduled time or in an unscheduled time. We don't have any of these things. So based on the arrival, we shall decide upon. So pattern is, we can classify that into two: static process, dynamic process. Okay. So arrival to the into the system, we can classify into two: static process and then dynamic process. So static process is controlled by the nature of arrival rate, random or constant. We can consider to be some random basis, or we can go ahead with custom, that is constant values. Dynamic means definitely it is not going to be the some standard. Okay, it is going to vary with respect to time, vary with respect to queue length also. Okay, so this when we go to supermarkets, what happens is there will be only one bill paying counter will be there at the end. By seeing the queue length, what the manager will decide is he will open up another bill counter next to it. So obviously what happens is the queue gets reduced. So based on the scenario, we shall decide upon. That is called as dynamic arrival. Static arrival means whatever may be the queue, only one counter means only one counter. They are not bothered about the arrival rate at all. So probability has to be considered. So here arrival probability distribution can be approximated by one of the following probability distribution. So Poisson distribution, exponential distribution, Erlang distribution. So these all are the three methods what we have got. Okay. So similarly, for the case of service, again we have got three more distributions, the same thing. So before we close this particular presentation, let us summarize. So we came to know what is a queue, how a queue length or waiting is going to induce the behavior of the customer, three types of mechanisms, three mechanisms of behavior we saw, where they don't join the queue, they join the queue and they leave the queue, and they migrate from one queue to another queue. So the aim here is only one thing: we wanted to have zero waiting time. That is, customer should never wait. Arrival irrespective to the arrival rate, service rate to be fast. So this is what our expectation. So for that we wanted to do a model. For that arrival rate and service rate, we have got some probability distributions. We just saw that, and with this we finish. So next we'll continue in the upcoming presentations. Thank you. So any doubts as usual, so kindly note it down in your notebook. We shall discuss the same in the offline classes.